Hi everyone, today we are going to talk about transactions and how to manage them in microservices. So let's start with a question. What problem do transactions solve? Imagine you are buying a cinema ticket. This process has several steps. Checking if the seat is available, processing the payment, and then booking the seat. But what happens if the money is taken from your card but the seat is not booked? Or the seat is booked but the payment never goes through? To prevent exactly these kind of situations where a group of operations must be completed together, we use transactions. A transaction is a unit of work that is either fully successful or fully rolled back. And if something goes wrong, we must perform a rollback. Well, when we talk about transactions as a single unit of work, we usually also talk about the ACID principles. In fact, they describe the rules for how this unit of work should be done. ACID means atomicity, consistency, isolation, and durability. So let's look at each of them more closely. Atomicity. This property says that all operations in a transaction either finish successfully or none of them do. It is the all or nothing rule. For example, you buy a cinema ticket, there are two actions, money is taken and a seat is booked. If something goes wrong, for example, the money is taken but the seat is not booked, the whole transaction is cancelled. This protects us from losing money without a ticket or getting a ticket without paying. Consistency means that after a transaction, the system must stay in a correct state. For example, we send money from one account to another. If money goes out from the first account, it must appear in the second one. The total amount of money in the system does not change, and this is what keeps the system consistent. Isolation means that transactions running at the same time do not disturb each other. They look like they happen one after another. For example, two people try to buy the same ticket at the same time. Thanks to isolation, only one of them will buy it successfully, and the other will get a refusal. This protects the system from errors. But in fact, we need to remember higher isolation makes the system slower. And durability. Durability means that after a successful transaction, its result will not disappear, even if the server fails or restarts. For example, if you paid for a ticket and got a confirmation, then even after a power cut or server crash, your payment and booking will still be saved. So, there is also an alternative approach called BASE. Actually, it means basically available, soft state, and eventually consistent. In fact, this approach gives up immediate consistency to get better availability and flexibility in distributed systems. By the way, it is often used in microservices where scalability and availability are very important. Let's check each letter one by one. Basically available. This means the system continues to work even if some parts fail. It still accepts reads and writes requests, but maybe with some delays or limits. This is different from ACID, where any failure cancels the whole transaction. Soft state. The states of the system can change over time, even without new input. It is not always fixed right away. For example, our system may not be consistent at the moment. One node gets the request, writes the data, maybe thinks with a few other nodes, but not with all of them, and still sends a successful response to the user. That means the state can be temporary and will change until full consistency is reached. And eventual consistency. This means that data will become consistent across the whole system after some time. In other words, sooner or later, all information will be shared across all nodes or microservices. For example, you send a message and it appears on all the recipient's devices not immediately, but after a short delay. So, now let's compare these two fundamental approaches by key criteria. Purpose. ACID is perfect for traditional transactional systems where data integrity is critical and every operation must be completed fully or not at all. For example, in banking or booking systems. On the other hand, Base is designed for distributed systems like microservices, where high availability and scalability are more important, even if this means temporary differences in data. Consistency. ACID gives strong consistency. This means that after a successful transaction, the data in the system is always in a correct state. But Base gives eventual consistency. In fact, data will become the same across the system over time, but right after an update, there may be temporary differences. This soft state lets the system answer faster and stay available, while full consistency happens later. For example, during database replication, updated data may appear on copies with a short delay called replication lag. Availability. The ACID approach may have lower availability because any failure during a transaction can cancel it and even block resources or part of the system. But Base focuses on basic availability. The system stays open for reading and writing, even if some parts fail. This is very important for applications that cannot afford downtime. Data model. ACID systems usually use normalized table interrelational databases. This reduces data duplication and makes validation easier. Meanwhile, Base systems often use denormalized tables, which are more effective for fast reading. So the choice between ACID and Base is always a trade-off between consistency, availability, and other non-functional requirements. And in fact, this choice must depend on the business logic and the system's needs. So we already talked about ACID and Base and even compare them. But actually, to understand better why in distributed systems or microservices we often have to sacrifice one thing for another, we need a more fundamental model. And here comes the CAP theorem. In fact, it says that in any distributed system we can guarantee only two out of three properties at the same time: consistency, availability, and partition tolerance. Let's look at each of them. Consistency means that all nodes see the same data at the same time. If an operation is done, then every next tweet will return the newest version. Availability means that every request gets a response, success, or error. The system cannot be silent, even if data is not yet synchronized everywhere. Partition tolerance means that the system continues to work even if the network between nodes is broken. In the real world, network failures always happen, so this property is basic for distributed systems. Now, according to the CAP theorem, we can choose only two out of these three. Let's check the options: consistency and partition tolerance. Here, the system is consistent and tolerant to partitions, but it loses availability. So if there is a network problem, the system blocks operations or returns an error to keep data consistent. For example, if one server cannot write data to another, it cancels the operation and becomes unavailable. This avoids having different versions of data. Availability and partition tolerance. In this case, the system is available and tolerant to partitions, but it loses immediate consistency. The system is always open and processes requests, but data may not be the same on all nodes right away. Each server accepts and processes requests even if they do not match with others. So temporary differences can appear. This approach is often linked to the idea of eventual consistency, where data becomes the same across the system after some time. But right after any update, it may be inconsistent. And last option, consistency and availability. That means the system is consistent and available, but not tolerant to partitions. Actually, this is not realistic for distributed system because network splits are inevitable. This option is more about monolithic systems or databases running on one server, where no partitions exist. For example, a traditional relational database like PostgreSQL without replication. In microservices and distributed systems, we always need to consider partition tolerance. The real choice is a balance between consistency and availability. And by the way, modern databases often let us configure this balance. Sometimes we need fast answer, and sometimes we need a single correct version of data. So, in microservice architecture, unlike in monolithic systems, where transactions are easy to manage inside one database, we face big challenges with distributed transactions. Let's look at an example. Imagine we have three different services: order, payment, and seat service. We want to buy a cinema ticket. From the order service, we need to do two things at the same time: book a seat and pay for the ticket. And here problems may appear. First, someone else may try to buy the same ticket at the same time. The payment can be successful, but the seat is not booked. The seat is booked, but the payment fails. For example, because of a network problem. These are typical issues we see in distributed systems: inconsistent states. Imagine the user paid, but the seat is not booked. Or even worse, the system sold two items when only one was available. This happens when services cannot keep the same state at the same time. Wasted resources. The opposite case, the seat is reserved, but the payment failed. As a result, the seat is blocked, other users cannot buy it, and the money does not match. Availability problems. In distributed systems, any service may fail at any moment. For example, the payment is done, but the service that must provide the seat is down. As a user does not get the service, and the whole system looks unavailable. And finally, coordination. In a monolith, it is simple: begin and commit, and the transaction is finished. But in microservices, we need to coordinate many independent services to make everything atomic and conflict free. This is much harder and requires special mechanisms. Let's move to the first mechanism: logs. They are not directly about distributed transactions, but it's still useful to know about them and their types. In fact, logs are about concurrent access to data inside one database. In general, there are two main types: pessimistic and optimistic. Pessimistic log. For example, imagine booking a cinema seat. As soon as you press buy, the seat is locked and nobody else can take it until the operation is finished. This gives order, but it can also cause delays or even deadlocks, where two operations wait for each other. Optimistic log. Here it works differently. Nobody blocks anything. Everyone works in parallel, and the check happens only when saving. If the system sees that someone has already changed the data, the transaction is rolled back and tried again. This is good when conflicts are rare because it lets the system work faster and scale better. Here is how the process works step by step. Each record has a version field, for example, a timestamp or a number. This shows the state of the record at the time it was read. When we try to update, the app checks the current version against the original version. If they match, it means nobody else changed the record. The update goes on and the version number increases. If they don't match, the app throws an optimistic login error. This means the update failed because of concurrent changes. By the way, both pessimistic and optimistic log are usually used for internal transactions inside one microservice. They help the service keep local data consistency. Now we already know about pessimistic and optimistic logs. They help to control access to data inside one service. But what if we have several instances of the same service, and in each one the same scheduler is running? Without an extra mechanism, all instances will run the task at the same time, and then we may get duplicated operations. To avoid this, we use Shadlog. Actually, the main idea is to provide one distributed log. One instance gets the right to run the task, while others wait or just skip the execution. In this way, we avoid duplication and get a controlled and safe scheduler run in a distributed environment. So, now we move to two-phase commit, which is one of the oldest protocols for atomic distributed transactions. In fact, it means that either all operations inside the distributed transaction finish successfully or none of them do. The protocol has two main phases: prepare and commit. Let's look at a sequence diagram with a simple example of buying a cinema ticket. Imagine we have order service, which starts the transaction and also acts as coordinator. Then we have the participants. payment service for the payment, and seat service for the booking. Start. Order service gets a request to buy a ticket. Prepare phase. The coordinator sends a prepare request to all participants. Each participant does its part. For example, payment service checks if the user has money, and seat service checks if the seat is free and reserves it temporarily. It is important that participants keep these chains in a temporary but stable state, so they can later commit or roll them back. Then each participant answers the coordinator with OK or not OK. Commit or rollback phase. If all participants says OK, the coordinator sends a commit command. The participant then saves their temporary change in the database and release the locked resources. But if any participant says not OK, or if the coordinator does not get a reply in time, it sends a rollback command. The participants cancel all temporary changes and return to the original state. As for implementation of two-phase commit, usually data is first written to the database with a status like pending. Then readiness is confirmed to the coordinator, and finally the status changed to success or failed. Of course, two-phase commit also has its downsides. Actually, it is synchronous, which slows the system because the coordinator must wait for all participants. Also, if the coordinator goes down after the prepare phase, it can cause problems. For example, resources in participants may stay locked while waiting for commit or rollback. Another limitation is that two-phase commit reduces heterogeneity. It is hard to use different databases like PostgreSQL and MongoDB in one transaction. Still, if you are new to distributed transactions, two-phase commit can be a good starting point. Its logic is clear and easier to monitor. And by the way, some classical relational databases like Oracle, Microsoft SQL, PostgreSQL already support two-phase commit. We already know that microservice architecture gives us distribution, and with it come the challenges of keeping operations atomic. Well, this is where Saga comes in. It is a pattern for managing long-running distributed transactions. Unlike classic ACID transactions in monoliths, which guarantee strong consistency, Saga focuses on eventual consistency. This means consistency will be reached later, not right away. Saga works as a sequence of local transactions. Each successful local transaction publishes an event, and this event then starts the next local transaction in the chain. If something goes wrong, there is a rollback mechanism. The key principle of Saga is a compensating transactions. This means that for every action in the Saga, there must be a reverse action that can cancel its effect. For example, if you reserved an item in a warehouse, but the payment failed, the compensating transaction will cancel the reservation. Another very important rule is idempotency. In fact, this means that doing the same operation many times should not create extra chains in the system. In practice, this is often done with an idempotency key. At the start of a transaction, the service tries to insert this key into a special table. If the key already exists, maybe because of a repeated request after a failure, the operation stops with an error, so it cannot be duplicated. By the way, monitoring is also critical in Saga. Each microservice decides to commit or roll back independently, without a central controller. So we need strong monitoring tools to see the state of the whole transaction. The main advantage of Saga over two-phase commit is that it does not block resources and can reach high throughput. In two-phase commit, the system waits for the slowest participant, keeping resources locked. Saga, thanks to its async and event-driven nature, avoids this, but still Saga can be much harder to implement. And if it is designed badly, it can shoot you in the foot. There are two main types of Saga implementation: orchestration and choreography. And now let's take a closer look at them. Now we move to orchestration. The main idea here is a central coordinator called the Saga Execution Coordinator, or SEC. It acts like the brain and controls the whole sequence of the distributed transaction. The main role of the SEC is to send commands to participants, wait for their answers, and if something fails, start compensating transactions for rollback. In fact, all the logic is in one place, so it's easier to understand. Let's look at an example a bit more complex than just buying a cinema ticket. Imagine we are placing an order. In this case, our order service works as a SEC. In a successful scenario, the client starts the process by sending a request to buy some stuff to the order service. Then the order service sends command from example to payment service to take money, to inventory service to reserve item, and to delivery service to arrange delivery. These services run their local transactions. After finishing, they send results back to order service. When order service gets positive answers from all participants, it confirms the saga as successful and the order is completed. Now let's see a failure scenario. For example, if delivery service is down, everything goes the same until the request to delivery service. But delivery service is not available during the transaction. After seeing the failure, order service starts compensating transactions. It sends a command to payment service to cancel the payment and return the money, and to inventory service to restore the items. After these rollbacks, order service informs the client about the failures. By the way, communication between the coordinator and participants can be synchronous, for example, via HTTP or gRPC, or asynchronous using RabbitMQ with queues for requests and responses. Main advantages: reliable and centralized control of all steps in the distributed transaction and their rollbacks. This makes it easy to track the process. Clear logic because everything is inside one component. But there are also disadvantages. Centralized dependency. The tech becomes a single point of failure. If it goes down and is not resilient enough, it can block important business processes. Growing complexity. The coordinator logic can become very complex when there are many participants or complicated rollback rules. This makes development and support harder. Extra costs. If SEC is a separate service, it adds overhead for deployment and maintenance. The second option is choreography. This approach is based on event-driven architecture, where services react to events published by other services, without a central coordinator. Each service has its own logic to react to certain events and to publish new ones. In fact, services control themselves, knowing which events to handle and what to do next. Advantages of this approach: high decentralization. There is no single point of failure like a coordinator, so the system is more resilient. Flexibility. Services can evolve independently as long as events contracts stay stable. And of course, disadvantages: harder monitoring. It can be difficult to track a long-running transactions through many events. Idempotency. Each service must be idempotent to handle events that may be sent or received more than once. Let's check a successful scenario. When the user starts an order, order service sends an event order created to the order topic. Payment service, inventory service, and delivery service are subscribed to this event. Payment service reads order created, processes the payment, and if it is successful, publishes an event, payment successful. At the same time, inventory and delivery service reads order created, runs their local transactions, and publish their own events to their topic. Order service receives the successful events, deducted payment, inventory deducted, and delivery scheduled. Then it completes the order and, if needed, sends an event order completed, which other services may react to. Now let's look at a failure scenario. The first step are the same. Order service sends order created, and payment, inventory, and delivery services read it. Payment service processes the payment successfully and sends payment deducted, while delivery service schedules the delivery. However, inventory service fails to reserve the item, for example, it is out of stock, and sends an event inventory declined. In this case, order service reads the events from payment topic, inventory topic, and delivery topic. When it sees inventory declined, it sends an event order cancelled. Other services that subscribe to this topic react by running compensating transactions, for example, refunding the money and canceling the delivery. Well, this is how a saga with choreography usually works. Well, now we move to the concept of change data capture or CDC. This is an approach that allows us to track and send data changes that happen in a database. In microservice architecture, where data is split across many services, CDC becomes a key tool for working with distributed transactions. Each microservice has its own database with local transactions. CDC records the results of these local transactions, for example, a successful payment or a failed seat booking, and then publishes these changes as events. By the way, CDC is not used only for distributed transactions. The main problem it solves is that in microservices, data is spread out and this makes aggregation and analytics much harder. Traditionally, this is handled by ETL processes: extract, transform, and load. These processes collect data from all sources, unify it, and load it into an analytic database or data warehouse. Actually, CDC makes the extract step much easier in ETL. Instead of polling the databases from time to time, CDC automatically capture and sends only the changes as soon as they happen. This helps keep the analytics system always up to date with very little delay. CDC messages must follow some important rules. Order. It is important to keep the correct order of messages because they represent sequential changes. Timestamp. Every message must have a timestamp. This is needed to track the order of changes and also to visualize data in analytical systems. Delivery guarantee. Messages must follow the rule at least once. This means a message can be delivered more than one time, but it will never be lost. Asynchronous. Messages are sent asynchronously, so they do not block the user who triggers the change. Now let's look more closely at the tool Debezium. It is a popular open source tool that automates the process of change data capture. The principle of Debezium is very efficient. Actually, it reads changes directly from the database transaction log without adding extra load to the main database engine. This works because Debezium reads the WAL file, which the database already uses internally for recovery after failures. By the way, Debezium supports many databases, including PostgreSQL, MySQL, MongoDB, and more. It connects to them using special drivers. The captured chains often look quite technical because they reflect the internal database operations, but Debezium sends them to Kafka for further processing, often through Kafka Connect. Debezium has many use cases with CDC. Analytic systems. Debezium is perfect for fresh data in ETL processes and in analytical databases. Instead of pulling the database from time to time, you get a real-time stream of changes. This allows you to build reports with the most up-to-date information. Monitoring and alerts. It is possible to track critical changes and react immediately. For example, by sending alerts or starting automatic action when a certain transaction happens. CQRS. This is a pattern we will discuss in the next lecture. Debezium helps keep the read model always updated with fresh data from change stream. Cache invalidation. When the main database changes, Debezium can trigger automatic clearing or refreshing of caches in other services. Well, today we looked at several important things. First, we talk about transactions as a single unit of work. Either everything is done or nothing is done. Then we compared ACID and base, strong consistency versus availability and scalability. After that, we explore the CAP theorem and the unavoidable trade-offs in distributed systems. We also saw how to control concurrent access with pessimistic and optimistic logs, and how Shadlog helps schedulers. Next, we review distributed transactions pattern, the classic two-phase commit, and the modern saga with both orchestration and choreography. And finally, we discussed CDC and Debezium, how database chains can be turned into events and used for distributed transactions, analytics, and CQRS. And here is a quiz. If you want, you can check your knowledge. Here is my social media, and thank you all for your attention. See you in the next lecture. Bye bye.